Hello, statistics class. I'm going to go over chapter 4, section 4, part 3, and we're going to look at the calculating the probability for intersections. The last section, last part of section 4, I should say, we did calculating unions. Now we're going to calculate intersections. How do you find the intersection, the probability of the intersection of two events? And what formulas we can use to find that. But before we look at that, we have to look at something called, or we have to define something, independent events. Okay. Now, last part, 4.4.2, we talked about mutually exclusive events, which is two events that if one happens, the other cannot happen if they're mutually exclusive. They share nothing in common. Independent and mutually exclusive are often confused, but they are two different things. Independent events, two events are independent if the sorry, let me just start over. Two events are independent if the outcome of one event has no sway on the outcome of the other event. Okay. Both directions. So A and B are independent if the outcome of A does not affect the outcome of B at all, and if the outcome of B does not affect the outcome of A at all. Okay, so that is different from mutually exclusive, where A and B have an outcome in common. Well, no, they wouldn't have an outcome in common if they are mutually exclusive. There's no outcomes in common. So an example of mutually exclusive would be if you roll a die, and one event is evens and one event is odds. So all the even numbers and all the odd numbers, there's nothing in common. Independent events would be more like if you're rolling a die and flipping a coin. Well, what you get on the die has no effect on what's going to be on the coin. Okay, so they would be independent. A lot of times when we're doing experiments, they will be dependent on each other, outcomes. An example here in the notes is a person being colorblind and a person being male. Well, because it's much more common for a male to be colorblind, then the person being male has an effect on whether or not they're colorblind. And an example of independent events would be, I had said the coin and the die. Well, this has just two dice. If you're rolling two dice, observer two, you're rolling two dice. The outcome on one of the die, it does not affect what the other die will have. Okay, so that would be an example of independent. Okay, if I'm going too fast through the notes, please just pause the video. But here's the important part of this. Right here, you'll see again, I'll pause that if you need to write that down in your notes, which you should be doing. Just pause my video. So probability of two this is considered conditional probability when the events are not independent. When they are dependent, or they're not independent, same thing. That means that the outcome of one event is affected by the outcome of the other event. Okay, so here's the important thing: probability of B, and we put this vertical bar A. And what this means is this is the probability of B given that A occurred. That's wrong. This is called the conditional probability of A given that B occurred. Then this should be A, and this should be B. Okay, let me change that. The conditional probability of A given that B occurred is A, then that slash B. I'm just going to I just want to check that real quick. Make sure that that was a typo and that I'm not misinformed. And I don't want to misinform everybody else. Just trying to find it here in the textbook. Bear with me for a second. The conditional probability of A given that B occurred. Yeah, sorry about that typo. Of A given that B occurred. Good, because that's what I have been thinking it was. So, probability of A given that B occurred, okay? So, the probability, the general multiplication rule, and we'll see an example of this in a second, is the probability of the intersection of A and B will be the probability of A times the probability of B given that A occurred, okay? So, for two things that are dependent on each other, if to find the probability that both of those occur, you need to find the probability that one of them occurs, and you can see I have it both ways here, and then the probability of the other given that the one occurred. So, well, we have an example here, but if, for instance, maybe I should just do the example, because the example is going to be similar to what I'm thinking of off the top of my head. In this example, there are 8 toys placed in a container. 2 are red, 6 are green, okay? Now, you're going to pull 2 things from this container, okay? The thing about this is, if you're pulling 2 things from the container, pulling one thing from the container affects what's in the container, okay? So when you had 8 to start, but pulling one out, now we only have 7. So it's going to change the probability of pulling of what you're going to get. By pulling one thing out, you're changing what's in the container. So it would be different if we had separate containers and we're pulling one thing from each container. Then it's not affecting what's in the container each time you pulled something, okay? But because it's the same container, I had 8 things, I pull one out, now I only have 7. So that's going to change the probability of what you're pulling out. That's what makes these events dependent on each other. And that's what this means. The probability of pulling A, okay, probability of pulling, and it's going to ask, what's the probability I pull both the red toys? And there are 2 red toys out of 8. So if I'm pulling the red toy out, I'm going to have 2 out of 8 chances, but then there's only going to be 1 red toy left, and there's going to be 7 total. So I'm going to change the number that it's over to 7. I'm going to change the number of items to 1, from 2 to 1. So that's what this part here means. Probability of B given A. So let's go a little bit more slowly through this problem. So the probability of pulling a red toy, I'm just doing a chart here, a probability chart. So since there are 2 red toys out of 8, there's going to be 2 out of 8. The other toys are green, so there's 6 out of 8. Okay, so what's happening here is after you pull one toy out, the second choice is going to only have 7 left. So I'm pulling a red toy out, so now I have 1 red and 6 green in the basket out of a total of 7. If I pulled a green toy out, I'd have 2 red and 5 green left in the basket out of 7. So the second choice is affected by what the first choice was, okay? What this looks like written out. So let's say A is the probability of 2 red toys are chosen, okay? So the probability of red on the first and red on the second, okay, will be the probability of red on the first, okay, times the probability of red on the second given that there was a red on the first, okay? So you see what's happening here? We are saying, what is the probability of red on the first? That would be this 2 out of 8. And then what is the probability of red on the second? Okay, well, we have 2 reds on the second, but only one of these reds on the second pull is a given read on the first. So we want to use the 2/7. All right, so we take 2/8 times 1/7, which would be 2 over 56, which would simplify to 1/28. Okay, hopefully this is making sense. That how the intersection works of two dependent events. What this gives us the ability to do, though, is we can find conditional probabilities given the intersection and the probability of the given event, the event that we need to know is given. So the probability of A given B is equal to the probability of A intersection B over probability of B, the given event. So if we know the intersection of the two events, what that value is, which is what we found up here, and we know the probability of the given event, we can find what the conditional probability is. This right here, this probability of A given B is equal to the intersection of AB over B, is what we had up here. It's this thing up here, except we just divided both sides by, in this case, divided both sides by A. In the top case, in this case, we divide both sides by B. Okay, dividing both sides by A, we have A intersect B over A is equal to B given A. Divide both sides by B here, we have A intersect B over B is A given B. Go back down here, see what I'm talking about. Okay. All right, here's an example, another example, one more example. Suppose that the general population are 51% of men and 49% women, and the proportion of colorblind men and women are as follows. So you can see here that 4% of men are colorblind and 0.2% of women. Okay, or I should say 4%. This is actually people colorblind. Yeah, 4% of the entire population is colorblind. Wait, what am I saying? 4% colorblind and men. 4% of men and colorblind are colorblind. Of the entire population are colorblind and men. 0.2% of the entire population is colorblind and women. Hopefully that makes sense. So if a person is drawn at random and so on and so forth, you can look at that chart. A person is drawn at random from this population and is found to be a man. Okay, so it's given that they're a man. What is the probability that the man is colorblind? So this is not. So you gotta. It's very. It can be very nuanced what they're asking here. They're not asking what is the probability that it's a man that's colorblind. They're asking what is the probability that it's a colorblind person if we already know that it's a man. Okay, so that's different. We're not pulling from the general population anymore. We're pulling from only men. So we know it's a man already. What is the probability that once we know we've pulled a man, what is the probability that it's a colorblind person? Okay, because like I was saying, for this 4% here is the 4% of the entire population that are men and colorblind. 0.2% of the entire population are women colorblind. Okay, so probability of A intersect B would be the 4%. This is just the, by the way, the formula for conditional probability, where A is colorblind, B is men. They gave us that in the problem, and probability of, we want to do the probability of colorblind given that it's already a man. So it's the intersection of those two, 0.4 over the probability of B, which is 51% of the population. Okay. So you put that in your calculator, graphing calculator, 0.04 divided by 0.51. It's going to be 7.8% chance. So So it's kind of like if so. For instance, let's say you're having a child. I don't know. Hopefully this example works. If you're having a child and you don't know the gender, all right, you don't know the gender. There's a different chance that that child is colorblind. Okay, there will be a 4.2% chance that that child is colorblind. Once you know, like you talk to the doctor, you're having a child, oh, it's a male. Well, now there's a 7.8% chance that they're colorblind once you find out that the child is male. Do you see the difference? Hopefully you can see the difference between that. The entire population, it's a 4.2 chance that a person's colorblind. But once you know the condition of, oh, it's a male, that changes it to 7.8% chance that they're colorblind. I don't know. Hopefully that makes sense. As always, you can ask questions. Okay, so another part actually, same example. Given that the probability? What is the probability of being colorblind given that the person is female? Okay, so the condition is that they're female. So this is going to be probability of A given B to the C, because it's we're using the complement of B to indicate females. If you're not male, you're female. Okay, so now we're going to use 0.002 for the intersection between colorblind and female, and we're going to use 0.49 for the number or the percentage that are female. Okay, on our calculator, 0.002 divided by 0.49, you find out that you're having a girl, and there's only a 0.4% chance that they are colorblind, as opposed to a 7.8% chance. Okay. Hopefully that makes sense, how those events, how those work. So one more thing here. Oh, there's another example. Sorry about that. I thought we were closer to the end than we were. Okay, so if two events are independent, they are not dependent on each other, like the coin flipping as well as a die rolling, or two dice rolling, the outcome of the one isn't going to affect the other. Two dice rolling, I should say. Then the probability of both of those happening is you just multiply the two together. There's no conditional. Okay, so the probability of getting snake eyes, is that what that's called? Two ones on two dice, is the 1/6 for one die times 1/6 for the other die. The one die does not affect the other die. Okay. If you're rolling three die, then it would be 1/6 times 1/6 times 1/6 if you're looking for 3 ones, and that would just go on. That would just continue to go on for as many things as you're doing, but all of them have to be independent for you to just multiply the outcome of each of them. Okay, so a football team is involved in 2 overtime periods during a given game. So there are 3 total coin tosses, beginning of the game at the beginning, and then at the very beginning of the game, and then for each overtime. Okay, what is the probability that they lose all 3 coin tosses? And each coin toss is independent of the other coin tosses. Okay, so first coin toss, you have a 1/2 chance of losing. Second coin toss, you have a 1/2 chance of losing. Third coin toss, you'll have a 1/2 chance of losing. You just find the probability that you lose all 3. You just multiply 1/2 times 1/2 times 1/2, because they are independent events. You have a 12.5% chance that you'll lose all 3. Okay. All right. So the bookwork is listed here. I'll have a PDF of that page posted so you can look at that, and that finishes up part 3 of chapter 4, section 4. Thank you and good day.